Hello and welcome back to Calculus 1. We're starting chapter 3.1 with a lecture on Intro to Derivatives. So calculus consists of three major ideas, limits, derivatives, and integrals. Now we're going to spend two chapters talking about derivatives. Well, before we do that, we have to go back to our algebra and some stuff that we skipped in 2.1 that are actually going well with what we have here in 3.1. So what I'm going to do is I'm going to draw a function, f of x, and I'm going to put a point over here.
Professor? Yeah, it looks like the screen went down for whatever reason.
Point P.
Oh, we're back.
That's because I looked at it. Be afraid. Be always afraid. So we have a point P, and that's going to be a fixed point. Okay? Now, if you have a fixed point, we generally give that point a f of a location because it's a point that is fixed and its value is known, like let's say 3 and 15, whatever. And then we have a different point over here. We'll call that point Q. And as soon as you have 2 points, you can stretch a line in between. Now, I'm going to label point Q as x and f of x, obviously, right? Because that's going to be the output. So now, if you are looking at this line is called the secant line. Secant means in Greek to cut. So you see that this line slices through the function. So this line is a linear line, which means that it is going to have a slope. We can use algebra. We can use algebra to find that slope. We know that the slope is equal to y2 minus y1. I just taught this in my algebra class. y2 minus y1 over x2 minus x1. And we write that as m secant, right, which means it's the slope of the secant line that we see over there. Eventually that's going to catch up. No? Let's see. Yeah, I think we're having internet issues with the wireless, so everything is slow. Perfect. Perfect timing. Are we on? Yes, all right. So m secant is the slope of this line. And what I have is just a basic algebra formula, which now I am going to, since point P is a f of a, and point Q is x f of x, I'm going to plug those into my secant formula. So I will have f of x minus f of a divided by x minus a. So this is technically a pre-calculus way to write the same algebra formula, because now we are involving functions rather than just coordinates. So we improved, right? And now I want to do something. I want to let this x go to a. Remember how we are allowed to move things in calculus? So that means I'm actually sending this point Q to P. Well, that point Q is going to travel through time, and we can take snapshots of all of these tangent lines. All of these tangent lines we can find, because this Q is going to move. Every time we take a snapshot of Q, it's going to have different values which we can plug in here and calculate the slope, because we always have two distinct points, P and Q, or Q1 or Q1000, whatever. So now, as the point Q progresses along this line, there comes a time where P and Q collide, and they are the same point. Can you calculate the slope? Why not? Why can't you calculate the slope? What's the problem?
Or if Q equals P, then you don't have two different values.
Where? That's good. Where? I don't have two different values. Where? What is the thing that I can't compute in mathematics? Ah, 0 in denominator. Good. You see that the denominator is x minus.
So
Do you see that when Q collides with P, x and a are the same value? So if that's 3, 3 minus 3 is 0. So can algebra compute the slope? No. But if you look at these lines, you clearly see that there is a line over here. It's a special red line. So the black line is the original one. As the Q goes, it's gonna become all of these infinitely many blue lines, and then the Q is gonna collide with P, creating this special unique red line, and then Q is gonna pass, creating more blue lines. So there is infinity of blue lines that we can always compute, because the 2-point calculation from algebra will work. There's only one red line, and that red line is when P and Q are in the same spot. Well, as you are guessed it, that's the only line we care about. All of the blue lines are 2.1. We only care about the one we can't compute. Nice, right? How would you go about computing the value of the red line? Yes. Aha, we're getting infinitely close. So which concept do we use to calculate you going infinitely close? Limit. Nice. So this so important line will be the center of our Calculus 1. It's called the tangent line, and it measures instantaneous change. So this red line is called the tangent line. And the slope of that tangent line is calculated by the limit as x goes to a of the secant one, which is f of x minus f of a, divided by x minus a. So that's the theory. That's the theory. Remember that the limit never computes at the point. It computes infinitely many points before, infinitely many points after. They can be as close as you want to the point in question. You never compute at. That's perfect. Because once our x hits this a, you can't compute at the point because it's the zero in the denominator. But the limit doesn't care about that. Limit looks at all of the slopes before, all of the slopes after, and says, well, that's the slope you want to, because the trend tells me that that's supposed to be the slope you want. So we have now established a way to calculate the tangent line. Can you use algebra? No, right? Now, just to appreciate calculus a little bit more, please realize that we just computed a slope of the linear line at one point, right? Weren't you taught that if you have a line, it has to be supported with 2 points? Have some emotion. Where's the applause? You look terrible. Terrible. I'm leaving. Guys, you're calculating the slope of the line with 1 point given. Right? For 15 years, people said, no, 2 points. Well, now, 1. Right? So, we have a way to calculate the slope of this so special tangent line. Tangent line, still red. Tangent line measures instantaneous change. Now, all right, so it measures instantaneous change. We have to talk a little bit about this. You can measure the average change after the change process has ended. For instance, there is a point when baby cries for the first time, right? It's out, smack, wah, right? Okay, that's the beginning. Now, you look at that kid maybe 7 years later and said, wow, you've grown, right? Going from being measured in horizontal units to being measured in vertical units, right? So now you can talk about the average change in height for that kid in the period of 7 years, right? So that would be the average change. But see, the kid was growing at every point in time along those 7 years. That's the difference between average and instantaneous. If I can measure the instantaneous, right, I will be able to say how many inches per hour or day the kid is growing, right, at every moment in time. And that's instantaneous. The average is to say, oh, it went from this many inches to this many inches in 7 years, divide the number by 7 and say this many inches per year. Another idea that we use to describe the difference between the two is driving. If you go from your house to RVCC 20 miles, in 40 minutes, I will say that your average speed was 30 miles per hour. How do I know that? Well, you covered velocity average. That's the secant line calculation. You covered 20 miles minus 0 on startup in miles, divided by, now 40 minutes in hours. 40 minutes is 2/3. So 2/3 of an hour minus 0 to begin with in hours. So this is 3 times 20 divided by 2. 3 times 20 divided by 2, which is 30 miles per hour. So we have the 30 miles per hour average speed. Now, what does this mean? Well, nothing, right? About your speed, I can't do anything from average, which is why I also find it ridiculous when a student asks me, oh, what's the average in a test? Irrelevant, because if the scores on the test are going from 38 to 107, like, how's the average of 70 helping you? Right? It doesn't, right? You might be the 38, right? Or the 107 for that matter. So, yeah, averages don't really tell us a lot in many cases. So what does it mean, average 30 miles per hour? This is what it means. The car was moving 30 miles per hour by your house and you managed to jump in. Every stop sign, every red light, every traffic or whatever, you just were plowing through with 30 miles per hour. And then getting here on campus, tuck and roll, right? Because you are not going too slow. It's 30 miles per hour at all times. That's what average means, all right? Which is why I said, if I tell you that the average on the exam is 76, but I also tell you that the grades are going from 38 to 107, that 76 is completely meaningless to you, right? Until you actually see the grade on the test, right? So, 30 miles per hour is the average speed at which you get from point A to point B. Now, your speedometer, that's instantaneous speed. You see, as soon as you touch the gas pedal or the brake, acceleration or deceleration, right? Then your speed immediately changes, right? You know, you're casually driving down 78, you're going 700 miles per hour. That's faster than an airplane, by the way. And you see the speed trap, right? You look at your speed. Doom, right? Doom. That is instantaneous. You get charged for instantaneous speed. License and registration. You were going 32 miles per hour more than you're supposed to. All right, and then leave. Grim example, but yeah. So, the idea is instantaneous speed is going to be your speedometer, and it changes as you touch the pedals. It is measuring how fast you are moving at every instance in time. Clearly, it's 0 when you begin your trip because the car is parked. Clearly, it's 0 when you park the car at the parking lot, right? It's hopefully 0 on a red light. It's hopefully 0 at the stop sign, unless you do the rolling stop. Never do the rolling stop in Texas. I heard a story from my friend where the cop said, you went through the you went through the stop sign. He said, he really slowed down, license and registration. When the guy gets the license and registration, he grabs the hand, takes the stick, bam, bam, bam. Would you like me to stop or go slower? So go do the rolling stop in Texas. Good luck. All right, it's the one story I heard. The rest is all, yeah, you went too fast. So you see that the collection of all of those speed up, slow down, speed up, slow down, speed up, slow down, right? That's gonna smooth out to a 30. But you know that you went 45 and you went 0 on the stop sign and you went 0 on the parking lot, right? And you went 45 on one road, 25 on another road, and so on. So the difference between instantaneous and average is one of the key points of our course. So we have to understand those things. Happens at the point. That's the point when you looked at it and you determined what it is, right? The same moment when you look at the speed and you realize the speed, that's the measurement for that split second. It happens at the point in time, where the average happens over the interval in time, right? In this case, if I'm talking speed, this must be the time axis, right, in hours. And then I can go and do miles per hour. So, secant line is the average, tangent line is that snap in time. Now, looking at the tangent line calculation, it's not really pleasant to do this calculation in this form. So what we do is we convert this in an easier form, and then we unleash 2.3 to solve problems. So we go and we say, I will let those of you interested in proofs, that's the cool one, it's calculation I mean, let age be x minus a. You are going to subtract a on both sides here in the limit, and now we have limit x minus a going to 0, because a minus a is 0, of f of x minus f of a divided by x minus a. So I have age over here, I have age over here. A is given to me because I'm looking for the slope at 3 or slope at 7. That's a, right? You see that I'm looking for the slope of the red line at a. There we go. I'm looking for the slope of the red line at a. So a is given to you. You know what a is. Find the tangent line at x equals 3. A is 3. So we have a's. So we want to eliminate this x. This x is no good, right? So let's eliminate that x. I eliminate that x by flipping this equation here and saying x is equal to a plus age. I simply move a to the other side. And now plug in. Slope of the tangent line, good effort, is limit age goes to 0 of f of a plus age minus f of a divided by age. Calculates the slope of the tangent line at x equals a. So let's take a look at example immediately, and you will immediately see that we are using 2.3 to solve this. By the way, does anyone recall this formula from anywhere in your life? Pre-calc.
Yeah.
Yeah, does anyone remember the name? That's much tougher. See, when you see something as completely useless and no one ever told you that is going to be the most important thing of your Calculus 1 course, right? You tend to do the grind of the problem for homework and say, ah, right? This formula is called difference quotient. And you learned this in your pre-Calc1 class, and you had homework on this, and you had to calculate this, and no one ever told you that it's going to be one of the most important formulas of calculus. So difference quotient, guys. Difference quotient. Difference, subtraction, quotient, division. Difference quotient. That's the name. And now we have a limit in front of it. So you did this in your pre-Calc1 without the limit. All right. Find the tangent line. Tangent line for the rest of the course is going to be TL because we're lazy. Find the tangent line at x equals 5 for f of x is equal to x squared plus 3. All right. I have to crank that formula, right? The difference quotient formula. M tangent is the limit. H goes to 0. F of a plus h minus f of a divided by h. Great. I know that a is 5. And I know what f of x is. So, M tangent is a limit, h goes to 0, of f of 5 plus h minus f of 5 divided by h. I have to plug in a. I know a is 5, so plug it in. And now we have to plug in the function as well, right? Well, f of 5 is easy, right? You replace x with 5, so that's going to be 5 squared plus 3, that's 28. Yay. F of 5 plus h is a different story. You're replacing your x with 5 plus h. You have to square that, and then you have plus 3. So now this is going to be 25 plus 10h plus h squared plus 3. And finally, f of 5 plus h is going to be h squared plus 10h plus 28. Calculation is the same like in your pre-Calculus 1 course. So now let's plug everything in. M tangent is equal to limit, there we go, h goes to 0. And now f of 5 plus h is h squared plus 10h plus 28 minus f of 5, which is minus 28 divided by h. Perfect. Well, the 28 kills 28, that's done. And you can see that whatever is left, you can kick out h, which will cancel in denominator. So limit, h goes to 0. You can kick h out. You have h plus 10 divided by h. And guys, this is the problem which you did. You did this problem in homework, unless you skipped it, obviously, in 2.3. We are not learning new calculation today. This is just reviewing now 2.3. What are the methods? Factoring, canceling, rationalizing, right? What is the method that we did here? 28 minus 28 is 0. Factor h, cancel. So factor cancel is the method that we used from 2.3 to solve the limit, which is chapter 2. So what do I get? I get this to be a limit, h goes to 0, of h plus 10, which is 10, because h goes to 0. It says so right here. So, in the end, slope of the tangent line is 10. Now, this was done for the function x squared plus 3 at x equals 5. How about we do the same thing for negative 3? So we use the same function, which is x squared plus 3, and then we're going to take a look at x equals negative 3, and we're asking for tangent line. I mean the slope of the tangent line, not the tangent line. We'll get the tangent line later. So m tangent. What is m tangent? Well, you have to do this from scratch. Right? The entire procedure from scratch. You go and you say, all right, f of negative 3 is 12. And f of a plus, no, it is a minus h, a plus h, I mean. So negative 3 plus h, which is negative 3 plus h squared plus 3. Always have to, when you do function composition, this is your x. Right, that's the x. So it's x squared plus 3. X squared plus 3, but now our x is replaced with a plus h, and a happens to be negative 3, so it's a lot of chasing around. What do I get? I get h squared. 3 times h times 2 is negative 6h. 9 plus 3 plus 12. Now we plug everything in the limit, so m tangent is the limit of h goes to 0. And now I have h squared minus 6h plus 12 minus 12 over h, and the same witchcraft we had before. Cancel 12's, factor h, cancel h, and you can do this. So limit h goes to 0, h minus 6 divided by h. These guys cancel, and we get limit h minus 6, where h goes to 0. We know that that's going to be 0, and the answer is negative 6. So m tangent is negative 6 at x equals negative 3. And we had this one at x equals to 5. So you did all this work, and then the boss shows up and said, I didn't mean negative 3, I meant negative 13, I'm sorry. Yeah, back to calculating from scratch, right? Or even better. Oh, okay, you got for 5 and negative 3, here are another 20, you know, that you need to have. That's not how work is being done, but, you know, it's as good as the desert island analogy, right? But you get the idea. Every time you change value at which you are looking for tangent line, the whole calculation changes, and you get a different answer at the end. So it's very inefficient. So let's try to be more efficient and define the slope of the tangent line by using the limit where h goes to 0 and say f of x plus h minus f of x over h at x equals a at the end. This formula is amazing because you don't have to use particular a. You are using x instead of a. So you are solving for all possible slopes, all of them, in one shot. And then, at the end, pinpoint which one you want. So if someone is changing their mind every 2 seconds, You just need to switch stuff at the end. You don't have to go through the entire calculation. Because remember, if I change the -3, -3 changes this line, changes all of this, and changes all of this, right? The procedure is the same, but all of the numbers are different. Just compare the numbers between the two examples, at 5 and at -3. Everything was different, right? We were canceling -28. Over here we're canceling -12. So functions change. The order of the function is the same. You get a second order polynomial, but the two functions are vastly different, right? It was age squared minus 10 age plus 28. And now you have age squared minus 6 age plus 12. So that's different. So now this is a way to solve for all m tangents at once. One calculation, right? I'm going to put this on a barbed wire over here on a cloud. Let's do a cloud. Really? So this is your main formula. This is your main formula. So now what? Well, we have our f of x to be x squared plus 3. So now I do the same stuff. F of x plus age is x plus age squared plus 3, which is x squared plus 2x age plus age squared plus 3. In general, your grade withers with this one. You forget the middle term. That's in general what happens. So pay attention, right? Make sure you have the middle term calculated. All right, so now limit age goes to 0 of x squared plus 2x age plus age squared plus 3 minus x squared plus 3 divided by age. I hope you see that these guys cancel. Positive x squared and negative x squared. Positive 3 and negative 3. Why, when you distribute the minus, both of these in parentheses become negative. You see that your leftover has age? Factor it. So limit age goes to 0. Factor out age, we're left with 2x plus age divided by age, and this is where age drops. Now you are left with the limit of 2x plus age as age goes to 0. So what's the answer for this limit? I can't hear, the air conditioning is squealing. What's the answer? 2x. Because age goes to 0. This air conditioning? It's annoying, but we'll live through it. Do you see what I got at the end? You know how earlier we got particular slopes? You got a formula now. So this formula computes all slopes. what do I have? If x is negative 3, m tangent is negative 6. If x is 5, m tangent is 10. These are the problems we did before. X equals negative 3 times 2 gives you negative 6. 5 times 2 gives you 10. You give me a number, I'll give you the slope back like this. So I invested a little bit more work to come up with a function which will generate all of the slopes that you can possibly have. All you need to do is to give me your x, and I will give you back your slope on the other end. Ready? What is the name for this function? It's the derivative. Have you learned new calculation? No. You better know this calculation, how to set up from pre-calc1 and how to do the limit from 2.3. The only thing that you are learning right now is that the answer of that is called the derivative. So, derivative is a function which computes all of the slopes of the tangent line. That's the derivative. The derivative is a function which computes all slopes of the tangent line. So that's what the derivative is. Notation. Is f prime of x or y prime or dy dx. There are more, but these are the ones that are mostly used. Others would be y with a dot on top. That's the original Newton notation for derivative, the dot. And some of the mechanical professors, mechanical engineering professors would still use such notation. You have d of a function. And now we have a partial derivatives. So dy dx, and you have capital Dx. And there are more. My favorite, this one. That's the Leibniz notation. These two are modified Newtons, right? To see how close that is. Instead of chasing the dots, you will put f prime for the first derivative, f double prime, f triple prime, and then it will switch into parenthesis notation. So this is the proper notation. Again, this is all in chapter 3 after the exam, so we don't have to worry about the green stuff. It's just I wanted to make sure you understand that, you know, even though there are more derivatives than just the first derivative, there is second and third and so on, it gets a little bit troublesome on chasing the dots, right? Plus the papers sometimes, you know, have the dot made in the factory, so that can confuse things further. So that's the notation. And we just learned that for function f of x equal x squared plus 3, the derivative of that function is 2x. Observe the way I write this. The line for the function, the new line for the derivative. It says function is x squared plus 3. The derivative is 2x. So don't play with fire to put over here equal 2x. What kind of garbage is that? That's a linear function. That's a linear function. That's a quadratic function. You're saying that the quadratic function is equal to the linear function? No. Right? So you have to go to the next line and you get to write that. Or if you're using the y equals x squared plus 3, then y prime is 2x. Right? That's the other way. Now, why do I like Leibniz notation? The one with these. We'll see more on why I like it. Right now, it's the only notation. This is just one of the reasons. And the only one we're going to cover today. So the reason why I like Leibniz notation is because it's the only notation that allows you to write derivative in line. So you don't have to go with two lines. So you would say that the derivative in respect to x of x squared plus 3 is 2x. So Leibniz notation allows you to put everything in the same line because the derivative of this equals the derivative. Are we agreed on that? Over here, function equals function, derivative equals derivative, and you can't put them together because that's the function, that's the derivative. Now over here it says derivative of this is this. Well, technically, the derivative is the derivative. So it's okay to use this notation in line. So this is one of the few reasons why I like this notation better than the one up there. You can use whatever you want. You can do 100% of your problems using this notation here. Correct answer is a correct answer. The only time when I get annoyed is when you go and put the derivative equal to the function. It actually happens in one case. Derivative of e to the x is e to the x. It's the only function, right, in the galaxy that has that property. So that's the only time, right, when you can write function is equal to the derivative for e to the x. Now we're going to cover that after the test. You don't have to take notes now. I'm not writing it. But I just want to make sure that you know that you can't use the upper notation for the inline writing. Only the bottom one. Now, I'm going to jump into 2.3 homework and show you these problems. What is the difference between me asking you 2.3 or 3.1 question? Guys, it's the same question. It's just the words that I'm using. If I say, find the limit of the difference quotient for x squared plus 3, I'm asking 2.3. Find the derivative of x squared plus 3, I just asked you the same problem with the words from chapter 3. See that? So if I say find the limit, you know what to do, it's 2.3. If I say find the derivative, you know what to do, it's 2.3, right? So it doesn't matter. Now obviously on the exam, I'm going to say find the limit, right? Find the limit. Even though I could say find the derivative. It's the same thing. Now, I'm going to jump to 2.3 homework. And we are going to spot these questions. Nice. Immediately. Oh wait, am I in the new book or am I in the old book? I don't know. I'm in one. Can you please take a look at page 80? and see if problem 47 is the problem 47 on the right side. Page 80 in a new book. There it is, yes, good. All right, so this is new book. This is not gonna match your MyMathLab, okay? But MyMathLab book has the same problems. So they're gonna be just in a different spot. Guys, look at 47. 47 is exactly the calculation we just did. Age goes to 0, blah, blah, blah. Now go down to 53, another one. Age goes to 0, boom. We did this problem, and I did it with 5. It was a different function though, right? Next one. There's at least 5 or 6 of these scattered throughout your 2.3 homework. 40. Problem 40. Right here. This is actually the derivative of 1 over x at 5. X equals 5. See that? So you can replace these 5s with x's and then do the problem, and then at the end you can plug whatever number you want, right? So you see that these problems that we just did in 3.1, they're all over the place in your homework. If I go to the next page, there will be more, if I remember correctly. I know I've seen one somewhere. It's somewhere over here. It's probably one of the word problems. So, calculation is 2.3. Let's review one more function. Let's do the 1 over x. And then take a break and then... wait, hold on. When is the class ends?
7:50.
7:50, yeah. So we do one example, take a short break, and then do the review for the rest. This is... your function is 1 over x, and you are looking for tangent slopes. Alright, so your f of x plus h is 1 over x plus h in a setup, right? Then we do the limit, h goes to 0, and here I have 1 over x plus h minus 1 over x over h. If you compare this to the homework example, those x's were 5s, right? It's the same problem. Now we're doing the general problem, so those 5s could be 2s or pi's, whatever, doesn't matter. What's the only thing I can do? Well, clearly combine fractions. So we are going to multiply by x and then x plus h. Don't forget to write the limit on every step. Like it's minus 1 per time you forget it. So it compounds to a lot of minus. So what do I have? Denominator is x times x plus h. I'm going to leave it like that. And in the numerator, I have x minus h. And I still have over h, and I can put over 1. These drop, and I have limit, h goes to 0, negative h over x plus h divided by h over 1, which goes negative h divided by h x plus h. And this is where h drops. You always have to figure out the way to cancel the h in denominator, because that's the one that's going to 0 and makes a lot of noise, right? That h needs to be eliminated, and there it is, finally eliminated. Now, I have limit h goes to 0 of -1 divided by x plus h. Well, we know that h goes to 0, so what's left? Exactly. So we just found that the derivative of 1 over x is -1 over x squared. So now your homework problem said, what's the slope at 5? -1 over 25, like this. Cool? Of course, cool, it's calculus. So, next time someone says, what do you know? Work that out. Ta-da! That's that. Bye.